Hi everyone, consider these two cases, case 1 and case 2. In the first case, I have a block resting on a horizontal floor, and in the second case, I have a block resting on my hand. This is my hand, okay? Here gravity is acting downwards. Now, what I am going to do is I am going to give this block an initial velocity, tick like this. What will happen? Well, we all know it will travel for some time and it will stop, isn't it? Similarly, here I will give this block an initial velocity by throwing it up. What will happen? It will travel for some time, and here also the block will come to stop. Now, in both the cases, if you notice, I have given some kinetic energy, right? If you give velocity, you are giving kinetic energy. Now, in both the cases, the body stops. That means the kinetic energy becomes zero. So, the question is, where did the kinetic energy go? Where did the kinetic energy go? Well, what is the difference between these two cases? In both the cases, it came to stop, but here it stops permanently, right? Whereas here it stops only momentarily. That means here, when the block is going up, the force acting on the block is gravitational force, right? So as it goes against gravity, it loses kinetic energy. However, that loss of kinetic energy is getting stored as potential energy. So when it reaches here, though kinetic energy becomes zero, it will store that kinetic energy as potential energy. And while coming back, that potential energy will be again given as kinetic energy. Let me give numerical example. So let us assume here the potential energy is 0, the height 0 location. So here what was the potential energy? 0. And what is the kinetic energy? Let's take 10 joules, which I gave. When it reaches here, kinetic energy becomes 0 and all that energy will become potential energy. So potential energy will now become 10 joules. When it comes back, the potential energy will again become 0 here and kinetic energy will come back to 10 joules. If you notice, the sum of potential energy and kinetic energy, the sum of potential energy and kinetic energy, which is called in physics mechanical energy, that energy remains conserved, right? 0 plus 10, 10, 10 plus 0, 10, 0 plus 10, 10. So mechanical energy remains conserved. That's why this kind of forces, in this example, gravitational force, where the mechanical energy of the system remains conserved, such forces in physics we say conservative forces. Okay. Now come to here. When the block is going this side, the force which is acting against the motion of the block is friction. Here it was gravity, right? Acting against the motion of the block. Here the force acting against the motion of the block is friction. And then because it stops permanently, here the kinetic energy of the block is completely lost. And there is no change in potential energy, right? The height remains the same. So that means from here to here, mechanical energy is lost. Unlike here. Here mechanical energy was conserved. Here mechanical energy is lost by the system. And therefore, such forces where mechanical energy is lost, that kind of forces in physics we say non-conservative force. So friction is what we say a non-conservative force. Here Because kinetic energy is lost, it is not stored as potential energy. That's why for friction or any non-conservative force, there is nothing called potential energy, right? You have heard of gravitational potential energy, but you have never heard of friction potential energy, isn't it? Now here is the twist. What is actually friction? Well, friction is not some mysterious force. It is primarily due to the electrical interaction between the billions of molecules of the floor and the block. So friction origin is basically the electrical force between the charges in the molecules of the block and the floor. Now some of you may think molecules are neutral, isn't it? So how can there be electrical force? Well, even if molecules may be neutral, there is a possibility that the plus charge and the minus charge of the molecules may not coincide. Such molecules are called electric dipoles. And you can see the minus charge and the plus charge are nearer. So there will be an attraction between these dipoles. Okay, of course the plus and plus may repel, but since minus and plus are nearer, there will be an overall attraction between the dipoles. I am soon going to make a video where I will derive the formula for the force between two electric dipoles. So don't be surprised if two neutral molecules electrically interact. And it is this interaction between the molecules which give rise to friction. So friction is like the statistical average of all these microscopic interactions, electrical interactions. Now to understand this in a simple way, think you and your friends are standing in two lines facing each other. And I ask you guys to shake hands. Now let's say only these two are shaking hands and others are not shaking. So it will be very easy for me to move this row against this row, right? It will be easy for me to move this line with respect to this line. However, if all of you shake hands, it will be difficult for me to move one row with respect to the other row, isn't it? So similarly, the shaking of the hands is like the electrical force between the molecules. And the force which I need to move one row against the other row is like the friction, which actually is due to the intermolecular interaction. Just like the reason why I need to push one of the line is because of all this shaking of the hands, right? So those shaking of the hands is what is giving rise to the friction which I need to overcome, right? But what is the twist, you may ask? Well, friction, I told before, is non-conservative. But this electrical force is actually conservative. So if friction originates from these electrical forces between molecules which are conservative, then how friction is non-conservative? Now think about this carefully. When I study the interaction between only these two molecules, the energy of these two molecules before and after the interaction remains conserved, something like this. And therefore, the force here is conservative force. By this I mean, let's say this molecule belongs to the floor and this molecule belongs to the block. Now floor molecule had, let's say, a small kinetic energy. Now this is moving, so this had some higher kinetic energy, right? More kinetic energy. So when this is having less kinetic energy, this is having more kinetic energy. So when this will pass on it due to the interaction, this may start moving faster and this will start moving slower. However, the total energy remains conserved, isn't it? So initially this was 2 joules, this was 4 joules. After interaction, this becomes 3 joules, this becomes 3 joules. So overall it is 6 joules only, isn't it? So that way, this system, if you take separately, the interaction between two molecules, that microscopic interaction is still conservative in nature. Now, if this is conservative force, why is friction non-conservative? That is because this block, if you see carefully, has ordered kinetic energy. Ordered. By ordered, what do I mean? All the particles here are moving together, isn't it? With same velocity. So it is a very ordered kinetic energy, right? Everything is doing the same thing. But as it moves, because of this interaction, microscopic interaction, that ordered kinetic energy is given to the kinetic energy of the molecules of the floor and the block itself. And that kinetic energy keeps getting transferred from atoms to atoms to all the remaining atoms, and then it is lost to the universe, right? So that ordered kinetic energy is lost into disordered kinetic energy in the form of these random vibrations and motion of the molecules of the block and the floor. Whereas here, the ordered kinetic energy of the block comes back as ordered kinetic energy, isn't it? So here, the ordered kinetic energy is stored as potential energy, which again you get back as ordered kinetic energy. But here the ordered kinetic energy is lost into this disordered kinetic energy of the particles, and that never comes back to this block. And in that way, there is no potential energy getting stored, and in that way, friction results in the loss of ordered kinetic energy of the block. So, if somebody says friction destroyed the kinetic energy of the block, you should say, yes, it destroyed the ordered kinetic energy of the block, the useful kinetic energy, right? Why useful? Because the disordered kinetic energy will be dissipated to the universe. So it is not useful. You are not going to get it back like here. And in that way, friction, we say, is non-conservative. However, if you could zoom and see the interaction between the molecules, you would find that though friction is non-conservative, microscopically, this non-conservative force is actually conservative force, right? Finally, I would like to let you know that this spontaneous conversion of ordered kinetic energy of the block into this disordered random kinetic energy of the particles of the system, which some people say heat, is the basis of what we say the second law of